Hi everyone, today we're going to be talking about topic 6.5, energy of phase changes. And so phase changes are quite simple. In essence, substances will gain or lose energy. Of course, this is in the form of heat as they change phase. And what we use to kind of visualize this is known as a heating curve, which is shown over on the right. And this shows temperature as heat is added to a substance. And so over here, for example, let's say we had this is a heating curve of water. Over here on our x-axis we have heat, and our y-axis we have the temperature. And so you can see here, during the point in time where water is a solid, you have a general increase in the heat as you increase temperature, or the temperature increases as you add more energy. And so temp increases as heat is added. Then when we go through a phase change right here, we see that it's flat. And for water in particular, this melting point would be 0 degrees Celsius. And so now what's happening in the flat region is that all of the heat is going towards the phase change. And so during a phase change, all the energy is being used in the change, and none is being used to increase the temperature. So while you're actually changing from a solid to a liquid or a liquid to a gas, none of the energy is being used to raise the temperature, and instead it's all going towards that phase change. And so you'll have a point in time where it's flat, and then once again, once everything is liquid, you'll have this general increase once again until you reach another phase change. Temperature of this phase change for water, of course, is 100 degrees Celsius, and similarly, it will be flat, and then finally, you'll go to a gas, and again, as you add more heat, the temperature will increase as well. One important thing to remember, as the temperature is increasing, the kinetic energy is also increasing because they're proportional to each other. So what this is saying is, while you're in one particular phase, kinetic energy increases, and similarly to what I wrote over here, during a phase change, the kinetic energy is constant. Now, the heat of melting and boiling, the heat of phase changes, can also be calculated using some familiar parameters. And so the heat of fusion is basically the heat required to melt a substance. We'll call this Q with the subscript fuse for heat of fusion. And related, there is also the enthalpy of fusion, or delta H of fusion, which can be calculated by taking Q of fusion and dividing it by the number of moles. Of course, Q of fusion, this should be in joules or kilojoules, and this will be over number of moles in mole. And another helpful way to remember this is basically equal to the heat released when you freeze a substance. similarly to the heat of fusion. Now the heat of vaporization is the heat required to vaporize, otherwise known as boil, a substance. And we can use the exact same nomenclature as before. Q, we'll use the subscript vap to say it's vaporization. We also have the enthalpy of vaporization, which is just the heat of vaporization over N, which has the same exact units as any other enthalpy, joules or kilojoules per mole. And this is equal to the heat released during condensation, or when you go from a gas to a liquid. And I should make it evident that up here we're going from a solid to a liquid. Or I apologize. When you're freezing a substance, you're going from a liquid to a solid. So let's do a very quick practice problem together here. In this problem, we're told that we're given the heating curve for mercury, and we're asked to calculate the heat to freeze 100 grams of mercury at its melting point. And so if we look at this heating curve over here, this is where we have the melting point. Since we're looking at the heat to freeze, we're interested in the heat of fusion right there. We're given the heat of fusion in kilojoules per mole, which is basically equal to delta H of fusion, right? If it's kilojoules per mole, we have delta H, not Q. And if we're looking for the heat, we are basically asked, what is Q? Now, if we're going to calculate Q, that's basically just equal to the number of moles times the delta H of fusion. We don't know the number of moles, but we do know the grams, and so we can calculate the number of moles from that. And so 100 grams of mercury, we just multiply it by the molar mass, or divide it by the molar mass, which is 200.59 grams per 1 mole. And then we know that we have, for our delta heat of fusion, we have 1 mole as the bottom. And then we have to remember here that what we're doing is we're freezing. And so when we're calculating the heat to freeze, we use negative 2.3 kilojoules rather than this 2.30 here. Now, the reason we use the negative number, of course, is because this is looking at energy added, and energy added is going to the right. Going to the right, we're going from a solid to a liquid. And so if we were going from solid to liquid, then we use a positive number. But since this is going in the opposite direction, we're going from a liquid to solid, or we're freezing it, we need to use negative 2.3 kilojoules per mole. When we do that math, we get minus 1.147 kilojoules, not kilograms, kilojoules of heat are required to freeze mercury. We'll talk a little bit more about this in class, but for now, that's all. Thanks, guys.